Thank you all for coming today. We have a special seminar guest here from one of our neighboring biomedical institutions, the University of Kentucky. We're hoping to use today's visit to try to open new pathways that our two departments can collaborate with each other. Our guest today is Dr. Guigen. Guigen?
Yeah.
Sorry. He is a professor at the University of Kentucky and also an endowed chair and chairman of their Department of Biomedical Engineering. Along with that, he's also a fellow in the American Institute for Medical and Biological Engineering. His research focuses on advancing bioengineering through a combination of experimental and computational approaches. And today, he is here to talk about direct molecular interrogation facilitated by a nanopore technology. So please help me in welcoming our speaker.
Thank you very much. This is my deep honor to have the opportunity to come here. Mainly, as the introductor says, where I consider not just neighbor, I consider our department as supposed to be sister department or brother, should be to that level. We're in the same state. Although I've been in this country long enough, I know this so-called in-state rivalry, and that should not extend to the academic success for our future student as well as current students. So with that said, I mean, this is something that's part of my purpose coming here. But also I want to say, actually, the first time I met with your chair, Dr. Alparza, was about a couple of years ago back in Clemson University. When I was associate chair there, he visited us. So basically, we have longer than just a Kentucky connection, I guess. So yeah, so in that regard, I'm relatively new to Kentucky, University of Kentucky. I actually came last August. So I'm relatively new chair, and this is probably a good news because I don't have any baggage, and I don't have any negative or positive connotation. To me, it's just a blank sheet that we really hope to build more collaboration with you guys and find new ways to forge some statewide initiatives and so on and so forth to benefit our students and the state, of course. So this is why I want to thank you again for the opportunity. So, and then I want to basically touch base. I want to talk to you a little bit about kind of, two ways maybe. One is to give you something about my research and also kind of driving about the, kind of my view towards bioengineering in general and why bioengineering is different and what's the difference require a different mentality. So this is hopefully to some of the students will get something useful out of this talk. So meaning that you may not just hear the scientific side, you may also hear something you don't quite usually get. And towards the end, if I still have some time, I have a couple of slides to show you our other faculties' area of work. So hopefully we can start somewhere, to build some collaboration as quickly as we can. So that's kind of a background, I guess. Let me see. This is working. Yes, this is working. So, yeah, quick overview. I would like to start something philosophically. Tell you a little bit about my view of engineering education. I often think that engineers tend to be proud of our rigor in training. Particularly the rigor based on reductive thinking as well as the inductive logic. So I will basically tell you what is reductive, what is the integrative engineering all about in my mind. And also, since this topic more on biosensing, I'm just basically using that as a starting point say, what is the challenge for current biosensing paradigm and how we can change that, and so on and so forth, and then, you know, tell you some interesting story that guides us to come up some new way of thinking, and yeah, something, and then this is something probably more, the focus of it's an electric double layer, EDL based biosensing technology, and that's actually useful for molecular detection as well as nucleotide detection or sequencing DNA down the road. So yeah, we also have actually other application based on those nanopore technologies. So this is basically the kind of overview. So first of all, as I mentioned, I'd like to tell you a little bit about my definition of a reductive engineering, or say reductive way of exploration. So we probably all know about this story, and some know, some may not know. So the whole story is basically, this is, for some you know, you probably know this is a kind of, you know, when you were very, very little, young, you heard this story. You know, basically just say 4 blinded people and they're supposed to touch an elephant and then describe the elephant. And then, you know, they end up with 4 different descriptions of what elephant really is. So this is kind of a story to tell, you know, young children, say this is, you know, not the right way to explore, right? But this is actually happening even to this day, we just don't realize. This is basically today's blind man touch elephants approach. You know, in the late 90s, early 20s, you know, DNA became so, you know, a topic of research. And then a lot of people get into this, and then, I mean, you can basically say, this is exactly like what I mentioned here. I'm not criticizing this approach. I'm basically saying, don't forget, this is the limitation we're facing. So if you're not satisfied with this blind man's approach, we need to do something different. So that's my message. And yeah, so basically this is the kind of message here. Okay. So that lays out the groundwork, and now the next question is, what can we do about it? You know. So one thing I like to propose is I call it integrative engineering. I recently have published this book, and of course, I mean, a lot of things on computational, so that's why I emphasize my argument about what is my definition of integrative engineering. Is that if you think about, you know, uses Zen's philosophy, you know, you guys probably heard a lot about Zen. You know, Zen is not about meditation. It's actually not about building your bedroom look like a more relaxing. Zen is also about philosophic way of interacting with our surrounding. So one thing, basically, the theme or the thinking of that is, say, supposedly the story goes, say, if you want to know a flower, you're not supposed to cut the flower, bring to your lab, and dissect, do all the experiment. Because after you cut it, pluck it, it's no longer the flower you want to know. So that's the philosophy of Zen. So basically, Zen's way of just say, leave it there and try to contemplate. So again, I mean, you probably know this is not something you would easily buy in the argument, right? I mean, you know, you sit there and contemplate, you probably still don't get much. So this is my way of thinking is that now computational way based on thermodynamics, based on biology, is readily available to us. So this should be the way, you know, basically my way of integrative would be just say, take advantage of the computational way and to understand from science, thermodynamics, and all those aspects, and then do experiment, and then, you know, try to couple those together. That's the definition of integration. And once you do that, and iteratively, of course, then that's the way we can actually really become a 21st century Zen master to interact with the world we're surrounded by. So again, so this is kind of give you two introductive concept. Now let's move on to say, why don't I mention this? Now this is the reality. Okay, so for those, some of you guys also do biosensing. When we talk about biosensing, this is kind of a so-called, you can call this paradigm. Current paradigm is basically just say you have to have some kind of recognition mechanism to catch the molecule or target, and then you have a transducing mechanism to produce signal, and basically that's the structure of all biosensors today. But again, think about it. You capture those, so you label those. This is kind of like a Zen's way of saying, you take this back to your lab to dissect. And also, this is not just for them. Mainly, the challenge is that, these non-specifics, and the sensitivity, as well as the durability and longevity, and all those issues. So basically, this is kind of a way that we need a different view towards that. So the question is, say, whenever we want to look for something new, we always tell another story called looking for a Eureka moment. Okay, this is why I want to tell you a Eureka story. That, again, for some of you probably heard that story. This is a story about very ancient story, 200-some BC. Okay, there's a famous guy, Archimedes. I don't know if you know this, have heard about this person. Very smart guy, and he was basically the mathematician, philosophy, and scientist, and everything in his day. And very smart. So one day, his king basically says, he commissioned a crown, but he kind of suspect that the goldsmiths may cheated him. You probably know this is basically the old Greek story, right? So then, he went to this smart man, say, find a way to find out. And he basically says, I have no idea. And then the story goes, one day he was in the shower in the tub, and suddenly he says he realized something. Basically used the water to measure the density, and so you can figure out exactly. So that the story is basically the Eureka is the story mentioning that at the moment he realized, he ran on the street, and this city is called Syracuse. Syracuse is the lower part of the Italy. Back then it's probably not part of Italy. This is a Greek territory, not a Roman territory. So that's the story that we all know about, okay? But this is not the story I want to mention. This is why I said this is usually the story half told. So what this guy is actually feel much more proud himself is actually that he considered himself the crowning contribution to the war was his discovery of this cylinder and the sphere. The ratio of both the sphere surface and the volume was the same ratio, 2 and 3. So that he considered that as his biggest achievement in the whole life. So before he died, he basically requested that this formula and this be carved on his tombstone. So that's how he viewed himself, the major contribution. So why I want to tell you this story? Well, mainly I want to tell you that, whenever you hear something, it's not just a story. You need to go a little bit deeper, say, why these two are related, and how this guy has basically come from one discovery leads to the other. Is there any correlation? So that's my purpose, to tell you this story. So then think about it. If you probably already start thinking in your mind, say, the way I mentioned earlier, the so-called engineering rigorous training is based on the inductive logic. inductive logic means that you have to be, you know, like logically step by step, and there's no missing link. So many times we're governed by that thinking. So when you think about that, the first question you ask is, how do you prove it? Okay, so now you think about it. If you actually go back to your high school geometry or whatever you know, you can prove it. You know, it takes a lot of time, of course. But that's the difficulty. This is the problem that for our engineers. Okay. And then if you think about abductive logic versus inductive meaning that you actually relax a little bit. You can, you know, say, if there's a missing link, so be it. You know, I will try to make the bridge to fill that later. So this is the logic, very important logic. So the question is, you're always supposed to ask how he thought of it instead of how he proved it. So now I think about it. He knows, you know, the volume easy, right? So if you think about it, he can actually pick up something look like sphere and put in the cylinder, use water, you know, he can actually quickly figure out the volume side. But what about the surface side? See, this is something you need to think about. Say, you know, this guy, again, about 1800 years before Newton, before calculus was kind of regarded as being discovered. And then about 1300 years after the pi was known to the world. So basically this is where he stands. Now think about it. If pi is known, we already know circumference of a circle. So like 2 pi r gives you the, you know, roughly that, or at least the proportional. Maybe they don't have this formula, but at least you know, something times radius or diameter. So now the question is, this is linear. So if you actually think about push to one more dimension, you actually can think about, you know, you can actually calculate surface. So here's the hint for you. For those of you interested, you can think about, you know, to calculate the cylinder area. Basically, again, you know, this is the circumference, and then it rotates respect to this centroid. Okay, so basically, this is the circumference times the 2 pi and then this distance. Okay, so basically, if you use this formula, you can, cylinder-wise, use this formula. And then same thing for a circle. You can actually use this formula. You don't have to use calculator to calculate the surface of a sphere. So this is the way that, you know, if you think along this way, you can actually already thought about the outcome, and then you can actually go back to rigorously prove. So the reason I want to emphasize that is in many times actually to leapfrog and see what the end goal or end result is supposed to be. This is a very important step, and that step requires you to have this abductive thinking logic. So this is why I want to retell you this story, okay? Because it becomes so important that basically the message is based on something we're familiar with, and try to push a little bit further and to try to leapfrog and then see something that it's not that obvious. This is the so-called process of innovation. Okay, now, again, I'm telling you all these, and now I want to tell you that this is just not the story, this is actually the practice also. So back then, we're kind of also working on many nanostructures and for sensing, for other purposes. You probably see those things in many other forms of nanostructure. You know, some people like call this nanopillars, we like nanorods, we like to call them nanopillars. So yeah, we can make those very sophisticated, good-looking structures, and then for us, as you know, as a biosensing, we have to be exposed to aqueous environment. And this is what happened when they exposed, because this is actually formed by physical vapor deposition process. So then we say, okay, now we find out why, okay, and there's a capillary force go against us. So this is one aspect, and then we come up with an alternative, okay, basically, which later we move on to an aqueous set process to form the structure. So yeah, so we solved that problem, solved that issue. And then we even went a little bit further, saying now we actually can form those integrated. You know, you probably heard nanostructure, you have seen those microstructure, but to integrate micro and nano, and this is something that even to this day, I think is still not widely done. I mean, this is still a lot of challenge, but this to me is also a very important steps. So you know, we overcome that, it looks very nice, and then we even go further and say, okay, we can even use them for cell interactions and guiding cell fates and so on and so forth. You know, we've done so much, and then move on to other type of sensing, basically use similar structure and then incorporate nanoparticles. So we had so much fun looking all of those, and then even build those into microfluidics devices, and then use those more added control to enhance the performance. So everything looks so good, you know, and then you could say, okay, we're done. So in this case, we're not done, because one thing puzzling or bothered us was, say, since we're talking about nano, right? So when the size goes down, and we realize that this is based on the known theory back then, and then when the size goes down, and the measurement actually deviates from this so-called known theory. And this, you know, for some maybe it's okay, you know, it doesn't work, we can forget. For us, I don't know, for some reason, we're kind of bothered, we want to find out what happened. So then we dug into, and more we realized we called attention to this, called an electric double layer. Now, for those of you who heard this term, this is actually nothing new. Again, this term has been defined almost 100 years ago. So again, regarded as something everybody knows, or at least the people who studied know, supposed to know this. So then we look into that a little bit deeper, and we realize that this is actually not the case. Not really like we know about it. You know, this is basically at that time, or even to this day, this is basically the three known theory about electric double layer. Okay? That's all we know. And then if you look deeper, you realize actually there's a lot of issues. You know, these theories, you know, every time somebody develops a theory, they make a lot of assumptions. And sometimes the assumptions are reasonable, sometimes the assumption may be bad. Okay? So one thing is there's no electron transfer across the surface, and then all ionic species in the solution is supposed to follow the Boltzmann distribution, and then, you know, electron neutrality always apply no matter what. Okay, so basically this is kind of assumption that developed this. Now so in our case, we don't see that. So basically, this is where I mentioned the computational as well as the experimental integration comes in. So we basically say we have to go back from scratch. But again, go back from scratch, go to 100 years back. Again, you would just do things on paper. And this is the actual problem. When you do things on paper, you make a lot of assumptions. So again, this is because we're now much later. We're not that much smarter now. I don't claim that, because we just simply have computer software or you know, computational capability to us. So we take advantage of that. We basically re-examine the whole thermodynamics behind it, and we don't make any assumption. We basically allow, you know, electron transfer. We don't even apply Boltzmann. And we just say these are the fundamental governing principles. And then we solve them, you know, and then once we solve it, we realize that, you know, there's some issue. So for example, one thing particularly is that if you say like, this is kind of like say, if the double layer relative range is say, you know, if double layer, yeah, if your size of electrodes is small versus larger, and the effect becomes so prominent when the size, the physical size of the electrodes or the nanorod goes down. So basically, this kind of confirmed that double layer is contributing to the difference that deviates from the so-called theoretical prediction. So, and then we go on a little bit further, say, okay, now we also then see this is a final element, you know, continuum level, and then this is a molecular dynamic simulation, and these are our experiments. So one thing we find out, remember I mentioned that in the theory you are not allowed for electron transfer, and there's no electron transfer, you actually have this curve. Now here, when we don't have electron transfer, we have this curve. It's kind of like agree with this. And this is pretty much the Boltzmann. But when we do allow electron transfer, we'll see this behavior, okay? And this is actually 1947, Graham is the one that measured the double layer capacity. And he actually captured this behavior, but no one following him was able to explain. And unfortunately, he was also died early, you know, he did not actually complete it, you know, he was probably some accident or something, that he actually passed away early, so basically no one follow that. So basically, the point I want to make is just based on the computation, we already know that this is actually not due to leakage of charge. And then we did this. When we put some redox in our solution versus no redox in the solution, then you can actually also capture these in the measurements. So this is kind of a confirmation of saying, you know, even though the so-called electron double layer is supposed to be known for over 100 years old, we actually don't know that much work. So that's the important message for us to think about. And now what are we going to do with it? Now we basically say, okay, we kind of revisit the theory and we find a couple of holes and we maybe see some potential. But what are we going to do? So here's what we're going to do, because we're actually looking for something for sensing, right? I laid the ground early. We actually don't like all those labeling technique. So we want to just say, hey, now can we use this as a new paradigm for biosensing? So that's the question. And now, of course, it's, you know, you have to do some quick so-called pilot study or tryout. And, you know, we basically say if we change the size, we actually can see the capacitor does change. Also, if you change the compact layer, also you see change. And also say the concentration of electrolyte. So everything we kind of preliminary try all points to the possibility that EDL can be a means to do detection. So then we kind of run this, you know, a simple test. Okay. So this is basically a measurement. So for people who do electrochemical measurement, this is the typical curve you probably measure all the time. You know, it's called a cyclic voltammeter. And now this is the red color curve. Is basically is a different type of voltammeter, if you wish. This is more like a capacitance versus current. Okay, voltammeter you measure current. So in our case, we measure capacitance. So if you look at this two curve, basically they capture the same process or same events. But the key is that this curve actually captures something that it was not reflected in the typical voltammeter. So this is about the features. For example, like here, it's supposed to be there's a water molecule orientation. But if you look at here, there's something happening here. Okay, but you know, this is because there's two things going on. Okay, you have hydrogen adsorption here, and then there's something around here. but also it's kind of overshadowed by this big reduction peak. And here, this is even more prominent. In the CV, there's only a small hump, but here, this is like a sharp, V-shaped turning. So what are those features? You know, basically, I mean, the first one is kind of capture this event, you know, people captured by, say, you know, by changing slightly the potential, the biasing of the electron surface, you can actually kind of force the water molecule to rotate. And this is a simple test that actually can capture that event. And then for the second peak, this is probably the events that here is capturing the adsorption happening on the surface. Basically, you can actually see the mass change of this behavior. And the last one is actually here is mainly about the lattice formation on the surface. Okay. And again, these are not visible in your traditional CV, and that requires something different way of measuring. But this becomes so important. So that's why it actually leads to now, you know, basically, this is a kind of way of saying, you know, in the beginning we're looking for Eureka moment, now we feel like we found one. And this is actually a pattern technology a couple of years back. We're now actually pushing this even further. So now the challenge, of course, is that you have to, you know, to take advantage of the electric double layer. You have to bring molecule into the double layer domain. Okay? So that's why at the same time, this nanopore technology is also picking up a lot of steam. So we actually also take advantage of the nanopore. Nanopore just say, you know, in the memory you have a pore of the nano size. This is about 10 nanometer size, and it's about 150-ish. So that's, you know, and if you guys are familiar with nanopore technology, there's many different types of nanopore. But ours is probably the most simplest nanopore because we actually don't need anything else. All you need is just the pore structure and then some electrodes, you know, basically the coating of the metal contact. That's all you need. Okay? So basically this is now our base for biosensing, you know, and the EDL nanopore biosensing. So you can actually do a lot with this kind of basis. Okay. So one is you can feed those analytes into it, and then you can actually pick. So in our case, we actually can pick both the voltage. This is the double layer potential, as well as the so-called blockade current. And this is typically, I would say, probably 90% of the nanopore technology out there only measure this current. And this current, to some, particularly to me, is not that reliable. Okay? So, but we still measure that as kind of a auxiliary extra information. But we mainly rely on the double layer potential measurements. So give you a sense that, you know, say if this is actually, I think this is about the 20 nanometer pore versus 5 nanometer pore. So if you just reduce the size of the nanopore, you also see the signal noise will reduce significantly. So here, you know, you actually see a lot higher deviation, but when you have a much smaller pore, you know, the deviation suddenly kind of reduces. And this is also the importance of refining the size of the nanopore, particularly in our type of a nanopore technology. So, and the other benefit is that because we do multi-signal measurements, and we also recently added mobility measurements. So basically in that case, you can actually do multiple target measurements without even label any of those. Okay? So you basically, you know, this is kind of a predictive versus the actual situation, and then you do 3D kind of data analysis, you can actually kind of capture, because prediction means, based on your measurement, you can predict which signal is from which target, and then you compare. So, in a sense, we're getting very close. I should say this. And even more interesting is, say, we also try some nanoparticle, basically try to oxidize the nanoparticle and reduce it. So the only difference between these particles is one is oxidized, one is reduced. And then you can see that the measurement from the nanopore actually sees dramatic differences between these two different states. And that's another way of demonstrating the sensitivity of our nanopore. So this is one way to look at it. And now the other application is this. I call it Nanopore Transistor. Transistor, the purpose of transistor is for gating, right? But basically for switching purpose. So what do I mean by gating? See here, if we have actually a conical shaped nanopore, you can actually gate, you see here, these are positive biasing, and here's the negative biasing. See, in the positive biasing region, actually you don't get much of a conductance or current moving, but only in the negative. For those you guys have still remember these electrical concept, this is basically the performance of a transistor. Okay, so the nanopore can also be used as the nanopore as a transistor for gating, for switching purpose, and also recently we modified this slightly by using, instead of a conical pore, we actually add a membrane, very thin membrane here, near the channel. Okay. Again, this is nano size, but it's a channel, longer channel. So by adding a layer, in this case graphene sheet, we actually also use the charge on the graphene. We actually can control the gating, or say if it's a transistor, this is kind of like an amplifier, right? Amplification factor. You can actually tune the slope by different charges. Here we basically have these different charges on these sheets. You can have a different rate. So this is a further expansion of the nanopore gating switching mechanism. And then there's also, this is even newer data, the oscillator. Again, similar nanopore, okay, back to this nanopore, but now we're actually using a chemical process, okay? This is kind of like a spontaneous process to serve as kind of a redox happening spontaneously, serve as a kind of a clock to adjust the pH. And then that actually drives the current flow back and forth. So this is what we call the chemical oscillator, okay? Liquid oscillator, liquid transistor. So this is why I'm getting more excited about this technology, nanopore technology. Okay, how much time do I have? Good? Yeah, so now I'm trying to give you another kind of sense of because I'm for big integrative, and integration has to be relied on a lot of computation. So this is also kind of a area we want to expand, or some we have already done, meaning like biomedical devices, or even the physiological part of the body, and devices. These are stent devices or external fixation devices, and these are the vessels. Yeah, so these are the highlighted area, and the other area would be something more like a device side. Let's see if I can get it. So again, computation, integrative or multi-physics computation can allow us also to design. I don't know if you guys are familiar with crystal structure. Crystal structure has a different crystal orientation. Actually, different orientation can affect different way of wave propagation. So for this case, imagine like say, when we want to develop a sensor, like just use the nanopore sensor. Think about it, if I want to attach a remote mechanism to the sensor, I would need something we call a wave propagation and so on and so forth. So then you have to design a device that actually propagates by taking full advantage of the so for example, these are the cases just show you that you can actually see that these are different so-called different crystal orientation, and then you can see, you know, anything else is the same except the crystal orientation is different, and you already see that this case the propagation still goes strong, and this is already dissipated, you know, already chaotically. But here you can actually also see this red curve is like this case, and this is all. And for people design filters, this is also useful technology for that. You see somebody leaving, look like they might have cars, so let me wrap up quickly. Yeah, I can skip this one, and also this one too. So yeah, I'll just say in closing, I mean, I hope that now you get the sense what is the reductive versus abductive, and then integrative approach is so helpful. I mean, you know, I would tell you that several of our recent patents actually initiated from that to begin with. Okay, but again, computation alone is not sufficient. You still have to do a lot of experiments to validate, to confirm, and sometimes to realize. Okay, and yeah, I can skip that part. So yeah, I mean, in the department, actually, we have people working on bones, we have people work on, you know, musculoskeletal and biomaterials, and neural area, cardiovascular, optics, yeah, biophotonics, and so on and so forth. So I guess just stop here and for some questions.
When you were showing the high noise, especially when you had a high noise to signal ratio, and since you already have a model, have you thought of using like a Kalman filter or an external Kalman filter to try and track if certain events have taken place? Because that would be one of the potential applications of using this nanopore technology as well.
You say use external, like a
so let's
filters?
say, yeah. So let's say you have a nanopore, and you have a lot of noise, and you have a very good model, computational model, and let's say you want to realize that something has passed through, and you can differentiate the signal from the noise. You have a model-based filtering methodologies.
Yeah,
and you
yeah,
have
yeah. Good point. Yeah, we actually did that. Yeah. Yeah, this is, actually, I did not have the result. We do have a model that actually can consider simulated particle goes in, and the simulated particle can also push away the surrounding electron. Yeah, okay. That's a very good point. Yes?
The slide where you were able to discriminate between different species with the nanopore,
Yeah.
could you go over again how the differentiation was done?
So that is what I extracted from my thing.
Then you were asking this one?
Yes, sir.
Yeah, yeah. Well, first of all, for our measurements of the setup, basically, we can measure two signals, double layer as well as the conductance. But here I only present the double layer signal. So how do we, this experiment is basically say this, you know, we have a base, we call it base electrolyte or solution. This is the solution. we did this at various different concentration of sodium fluoride. And then we introduced this 4 different targets. Basically, this is a very small molecules. And so this is about a nanopore of 20 nanometer size. So you just, every experiment at every concentration, every different acid, every target, you do this measurement. And then, of course, you know, statistically, you plot this curve.
So are you measuring all 4 analytes simultaneously?
No, no, in this case, separately.
Oh, okay. I was wondering how you got, how you could
Yeah,
tell
no,
which
no,
one
no.
was
For this case, basically, yeah, this is one slice, but this took my student a lot of time.
Oh, I bet.
Yeah, as you can see here, you know, we have like almost how many dots here. Each of those dots means 1 concentration.
Right.
And each concentration, you run 4 different species. And then when we get down to 5 nanopore, you basically just do the same thing. Yeah, this slide is for that. But when you talk about multiple, actually, see here, we actually did multiple. Yeah. So the multiple is that the issue is this: predicted is based on the, you know, the kind of our computational model built along this capture or representing our measurement. But the catch is this: actually, the actual, you know, this code actually, at this point, we have not done this mixture yet. Okay, so meaning that this captured ones, this so-called actual ones, are still individually acquired.
Okay.
Yeah, but the encouraging news is that, you know, knowing this is basically just assuming we don't know anything. And we can still pretty much kind of, you know, deconvolute it in a way that they say, you know, if this cluster of signal actually from this guy, and it matches nicely.
Right.
But the real challenge, you catch a very good point. The real challenge is when we don't even have this. Now what we can do, right? So yeah, but I think you know, we now you see that we actually have not just on a current, we have a double layer, but on top of that, we also have a mobility. So this is the benefit. For now, we have 3 different means to measure, and so yeah, basically it's a resolving, like, you know, less in our base, I would say resolving mixture less than 6. We probably can do okay. Anything beyond 6 becomes very troublesome. That's the challenge we face now.
Thank you.
What end we like to send our speaker for his good talk, and I think the time is limited. We have to take you to the lunch.
Oh, okay.
Then
Thanks again.
Yes, we'll take our speaker to the lab. He will go to Tommy lab after the lunch, right? And
2:30.
2 labs.
2:30.
Yeah.